Hi, I am Harshita Anandabarathi, and I worked with Miss Mirren for my Talaria Summer Institute research. This summer, I focused on the impact of ocean acidification on nutrient bioavailability and primary productivity. So, here is some background information to start with. First, let's talk about our oceans and why they're so important, not just for marine life, but for the entire planet. Oceans are like the Earth's natural air conditioner. They play a massive role in regulating our climate and absorbing carbon dioxide from the atmosphere, distributing heat, and even influencing our weather patterns. In fact, over the past 200 years, the ocean has absorbed around 30% of the excess carbon dioxide that we've pumped into the atmosphere through activities like burning fossil fuels and deforestation. So, how does this all work? Well, the ocean absorbs carbon dioxide in a few different ways. Certain microorganisms perform photosynthesis, and as they do this, they absorb carbon dioxide from the atmosphere, and when they die, they sink to the bottom of the ocean, taking the carbon with them. Another way the ocean absorbs carbon dioxide is through a process called thermohaline circulation. This is where warm surface waters cool down as they move away from the equator and begin to sink. As they sink, they carry carbon dioxide from the atmosphere down into the deeper layers of the ocean. This is crucial because it means that the carbon dioxide doesn't just stay at the surface level of the ocean, but it also is pulled deep underneath, where it can be stored for long periods of time. And then there's the role of marine animals, especially those that build shells. These creatures use carbon from the water to form their shells, and when they die, their shells sink to the ocean floor, effectively trapping the carbon dioxide for millions of years. But the ocean's role doesn't stop at climate regulation. It's also home to the largest ecosystem on Earth, supporting a variety of life. Many species depend on the ocean to provide essential nutrients they need to survive, especially primary producers. These producers, like phytoplankton, are the first step in the food chain, providing energy to the rest of the marine life, from tiny zooplankton to large fish and even whales. Moreover, the ocean isn't just important for marine life, it's essential for humans too. It provides resources like seafood, salt, and many other minerals. Now, let's talk about something a bit more technical but super important: nutrient bioavailability. It's just about how easily and quickly organisms in the ocean can absorb and use nutrients. Primary producers depend on these nutrients to grow and to reproduce. Primary producers use sunlight, carbon dioxide, and other nutrients to produce energy through photosynthesis. This is called primary productivity, and it's essential because it's the first step in transferring energy throughout the entire food chain. But here's the catch: these primary producers need specific nutrients to do their job, iron and nitrogen being two of them. They're like the building blocks that allow these organisms to carry out photosynthesis and produce energy that fuels the rest of the marine life. If these nutrients aren't available, primary productivity will have a deep hit, and that can cause some serious consequences for the entire ocean. And now, ocean acidification. This is a huge issue in our world today, and it's directly caused by human activities. Since the ocean absorbs carbon dioxide, when there's more of it due to deforestation and burning of fossil fuels, they absorb an increased amount, causing an imbalance in the marine ecosystem. When carbon dioxide is absorbed by seawater, it reacts with the water to form carbonic acid, which is this equation, this reaction right here. And then the carbonic acid is unstable and then it dissociates into hydrogen ions and bicarbonate ions. The problem is this process produces more hydrogen ions than carbonate ions, and that leads to a drop in the pH of the water, which means the ocean becomes more acidic. This disrupts the balance of nutrients that primary producers need. For example, the availability of iron and nitrogen can be affected, making it harder for these organisms to grow and reproduce. This in turn impacts the entire food web, from tiny plankton to large fish and everything in between. But the effects of ocean acidification don't stop there. It also affects the animals that build shells, like corals and mollusks. These creatures rely on carbonate ions to form their shells, but since the ocean becomes more acidic, there is less carbonate ions that these organisms can use. This makes it harder for them to build and maintain their shells, which can lead to weaker structures and even death. And since many marine species rely on these shell-building creatures for food and for even habitat, the impacts of ocean acidification can cascade throughout the entire ecosystem. Well, all these topics together brought in my question for this research. How do changes in ocean pH levels affect the bioavailability of essential nutrients such as iron and nitrogen? And what are the implications for marine primary productivity? One part of this question is about how ocean acidification impacts these nutrients, specifically iron and nitrogen. These two are super important for the health of our ocean, but unfortunately, acidification makes them less available to the organisms that actually need them. Underwater primary producers, like phytoplankton, rely heavily on these two nutrients to perform photosynthesis and to grow. First, let's talk about iron. They need iron to create chlorophyll, the pigment that allows them to capture light and convert carbon dioxide into organic matter through this process. Iron is a metal that's really sensitive to changes in the ocean's chemistry. When iron is in its reduced form, known as Fe2+, it's more easily absorbed by phytoplankton. These tiny organisms rely on iron to carry out photosynthesis. However, when ocean becomes more acidic, this iron turns into its oxidized form, Fe3+, which isn't as bioavailable. This means it's harder for phytoplankton to absorb the energy through the iron that they need to grow and thrive. But that's not all. Nitrogen, another key nutrient, is also affected by ocean acidification. Nitrogen is crucial for all living things because it's a building block for proteins and other important macromolecules. When ocean acidity increases, it disrupts the nitrogen fixation cycle. The cycle is where atmospheric nitrogen is converted into more bioavailable forms, and this leads to a decrease in nitrogen bioavailability. This whole situation can lead to a process known as denitrification, where nitrogen is lost from the ocean because of the lack of oxygen. This is a big deal because it means less nitrogen is available for primary producers. When these foundational species struggle, it creates a ripple effect that impacts the entire food web. Iron plays a crucial role in maintaining primary productivity, especially in areas like the Southern Ocean. These regions have plenty of nutrients, but low levels of chlorophyll, meaning iron is already really scarce. Studies have shown that only about 1% of atmospheric iron, mainly from mineral dust, is actually soluble and available for marine life to use. The solubility of iron in seawater depends on various factors, including the presence of organic molecules that bind with it and pH levels of the water. As ocean acidification lowers the pH of the seawater, it reduces iron's solubility, making it even less available to the organisms that rely on it. This drop in bioavailable iron could have serious consequences, particularly in regions where phytoplankton growth heavily depends on this iron, which could trigger a domino effect throughout the ecosystem. As the oceans continue to become more acidic, these nutrient shortages could become more severe, potentially disrupting the marine ecosystems and affecting the global carbon cycle. This highlights the interconnectedness of ocean chemistry, nutrient availability, and health of marine life when it comes to iron. Nitrogen is vital for the growth and survival of marine life because it's a key component of amino acids, proteins, and nucleic acids, which are essential for cellular function and reproduction. However, as ocean acidification progresses, the availability of nitrogen decreases. This drop in nitrogen makes it harder for phytoplankton to maintain their growth rates, which can have a huge effect throughout the marine food web. One crucial process in the marine ecosystem is nitrogen fixation, where atmospheric nitrogen, also known as N2, is covered into forms that are usually usable, like more usable by primary producers. But here's the catch. Nitrogen fixation is heavily dependent on the availability of iron. A study analyzed nitrate concentrations in surface waters and found that many ocean regions it's actually the lack of iron, not nitrogen itself, that limits nitrogen fixation. This is especially concerning in oligotrophic environments where the ocean with low nutrient concentrations, like areas of the ocean with low nutrient concentrations. In these regions, low iron levels can significantly reduce the productivity of nitrogen fixing organisms, which are essential for supporting marine life. So, as iron becomes less available due to ocean acidification, it could severely impact the ability of primary producers to grow, which could disrupt the entire marine food web. In summary, ocean acidification poses a serious threat to the bioavailability of essential nutrients like iron and nitrogen, which are crucial for the health and productivity of marine ecosystems. As nutrients become less available, primary producers like phytoplankton struggle to grow and reproduce, leading to a cascading effect that impacts the entire marine food web. This decline in phytoplankton and zooplankton populations threatens the survival of larger marine species and disrupts the balance of ocean ecosystems, ultimately affecting global biodiversity and the carbon cycle. However, it's not too late to mitigate these effects. Reducing carbon dioxide emissions is the most effective way to slow down ocean acidification. These this can be achieved by transitioning to renewable energy sources, protecting and restoring carbon sinks like forests and wetlands, and adopting more sustainable agricultural practices that reduce the release of CO2 and other greenhouse gases. Additionally, supporting research and conservation efforts focused on preserving marine ecosystems can help us better understand and combat the impacts of ocean acidification. By taking action now, we can protect our oceans and ensure that they are good to support the diverse life forms that depend on them, including ourselves. The health of our planet's oceans is directly linked to the health of all living things on Earth, and it's our responsibility to keep these precious resources for future generations. Well, to end, I'd like to talk about my experience and my research with Talaria. For my research, I mainly use several papers written by professionals in this field. However, I also use websites to understand the basic chemistry behind some of these topics, such as ocean acidification, nutrient bioavailability, and primary productivity. And regarding my experience, I absolutely loved it. The mentorship system was great because I was able to learn so much from my mentor, and it was just great having her guide me through this entire process. And I really thank Talaria for this opportunity. Thank you.